Hi, so we are performing sign language detection through skin segmentation. I'm Saurabh, this is Dennis, and that's Kayo. So as you all know, the video sharing sites have become really popular, and everyone nowadays they share videos online, and people want to share their stuff through videos. And also there are also a lot of videos in sign language which are uploaded, and people want to be able to search for different videos in different sign languages. And usually the search engines rely on metadata and tagged videos to be able to search for different videos that are there. And so approximately 0.5% of the US population is functionally deaf. And as I mentioned, YouTube and all those other video sharing sites rely on these tagged data to find the videos related to what you're searching for. And right now the search engines are not capable of actually finding videos related to sign languages because they might not get appropriately tagged. So in our method we're trying to automate that process of tagging the videos for appropriate sign languages. So yeah, that's what we are trying to do. How can we improve the content for the members of the sign language community? Some of the related work has looked into this, but as the first method, they are capable of distinguishing between different languages, but the problem is that they work on controlled environment videos. So, in the real world scenario, you can have videos where the lighting conditions are different, the backgrounds may be different, and that will interfere with your accuracy. The second method is they use unconstrained videos, which is similar to what the real world videos would look like.
So in this work, we apply the skin detection algorithm in order to binarize all of our videos in the data set. And once we have all videos binarized, we use an SVM classifier to detect if there is or there isn't sign language content on that particular video. So this is the test pipeline of our application. So once we have the skin detect on the video segmented by using skin detection, we detect the faces. We detect the faces, and we compute the polar motion profile of each frame. And Kai is going to talk a little bit about polar motion profile later. So after that, we perform the average polar motion profile and feed this into an SVM classifier that is going to decide whether there is or there isn't sign language content on that video. Could you go? So this model is based on the Karapa work Saurabh mentioned, but instead of using the background model, we use the skin detection in order to perform video segmentation. So we do know that skin color is hugely affected by lighting conditions. So in our approach, we used a technique called gray ward in order to perform color compensation. And as you guys can notice, there are huge differences in the images before and after the gray wall techniques applied, especially in the background. And the second step is to generate a Gaussian model. So the Gaussian model for human skin color. In order to do so, we use this human skin color data set called SFA. And once we have the Gaussian model built, we evaluate the value of each pixel within each frame and check if the value within this Gaussian is higher than a threshold. If it is, we set the pixel to foreground, and otherwise we set the pixel to background. A parallel approach that we also perform is called skin map generation, in which we pretty much check if the value of the pixel within the frame lies within a predetermined range. And if in fact the pixel lies within this range, that's because the pixel is most likely color. So we set the pixel to foreground. Otherwise, we set the pixel to background. So with the outputs of the two previous steps I mentioned, we perform an AND operation, followed by erosion and dilation to get rid of noise.
All right. And then once we got the segmented videos, together with the face locations, we perform our experiments, and then we have two main steps for it. First, we need to train our skin models so we can use on the videos and segment them. And after we have the segmented videos, we would evaluate our approach on the classifier, the sign language classifier. So, as mentioned, we used the SFA skin dataset, and it has more than 3,000 images, and they have in different sizes. We use the 35 by 35 pixels, and based on those samples, like they represent peoples from like all races and colors, and based on these images, we computed a histogram, and then we created the Gaussian based on the histogram. So after that, we segmented the videos, and then we used the classifier to see how it performs. And to ensure a fair comparison, we used the same environment to do the classification tasks using our approach and using the original approach, the background-foreground segmentation. So the data set we used was made of 112 sign language videos and 120 non-sign language videos, and they were all gathered from YouTube, and they were representing different scenarios with different backgrounds, different illuminations. So it is a very diverse data set. And we computed precision, recall, and F1 scores, and the reported measures are the average of 1,000 iterations, and on each one of those iterations we do a random subsampling on the data set. So we select different training set size, and we randomly select on each one of those iterations. And our support vector machine uses RBF kernel, and it's on this SVM that we do the classification. So this was the histogram computed from the skin data set. As you can see, the axes are the chromatic red and chromatic blue. As you can see, skin tones, despite of people's color, are very strict. They are very concentrated on this area. They're around like the middle point on CB and CR chromatic space. So based on this, we computed the Gaussian model, and based on this Gaussian model, we segment the video doing the end operation with this other approach that we mentioned. And then here is one of the frames of the videos. The A is the original frame. B is when we got the fixed ranges. As you can see, it's fairly accurate also, because those fixed ranges is based on the assumption that skin tones, skin color is fairly condensed on a particular area of CBCR. C is the output of our Gaussian model, and D is the end operation between B and C. And as you can see, like almost anything changes from the Gaussian model to the end, just basically some pixels over here are not on the end. But the Gaussian model is also fairly accurate. And then when we segment those videos and we perform the classification test, these were the results that we found. So we used training samples from 15 to 60 using 15 increments, and the bigger the training set, the better the results. So considering the 60 samples training set, when you compare to the original Karapa approach, using the background-foreground segmentation based on Gaussian mixture models, then we see that the F1 score is much lower on our approach, but we can take a look that recall is not that, like, it's fairly competitive, the recall, but this approach really suffers on the precision. And then if we taking a look on those segmented videos, we see that illumination really seems to be a huge problem for us. The videos on the data set, they were like gathered from YouTube, so they don't have like standard illumination. They have videos like, if I just pull out my phone right here and start recording something, the illumination is going to be pretty bad. So we need something more robust than the Gray-Word theory to do this illumination compensation in order for our skin segmentation alone to work properly. And taking a look on the results, we see that maybe a combination of the original background foreground separation and the skin models could prove to improve the performance. We have this video, and like this is using the skin segmentation, and it's a case where the original approach would fail. Like, as you can see, there are a lot of motion on the background because the camera is moving, the guy is walking around in the room, and then even though skin detection is correctly getting the foreground pixels most of the time. Like we see some noises on getting some pixels from his t-shirt, and this is mostly due to the illumination because we have some real spotlights on the end. But in overall, this is something that the current classifier can handle. Like this isn't, of course, good enough for the classifier to work on. So combining something where we get this type of skin-based segmentation after we got the background foreground segmentation is something that could improve. So the original approach would get all those pixels from the background moving, and we can then later tune them based on skin detection. So all the foreground pixels identified by our original approach would then be on our next step tuned according to the skin detection to get a finer grained and segmented video. Yeah, and that's it.
Questions?
So you seem to model the skin colors with unimodal Gaussian,
Yeah.
but it kind of seemed like there are two small additional Gaussians. Would that be worth looking into, or?
Yeah, like
Because they're very small, so I mean, I
yes, yes, like it could be a way, but like if we take a look on videos where the illumination is good enough, like those ranges seems to be enough. When we use the Gaussian, making the end operation with this other approach where we have fixed ranges, it gives us a fairly good approximation of skin. But like our biggest problem is with illumination. It's very sensitive to illumination, so we need to have a better approach to compensate the illumination changes.
So are there any other methods other than the gray world method that you have been using for compensating illumination changes or color changes?
We need to take a look on that. Prior to this one, we experimented using skin segmentation based on K-means, but it didn't pan out really well. So we changed it to this one, which performed better. So, but it's really tricky when we have a data set that is so unconstrained. We have a wild range of videos. So it's really tricky to get something that performs robust enough for all the videos that we have on the data set.